Hello everyone, welcome to this video entitled Tips and Tricks number 18, Improved Induction Motor Model. As usual, I want to thank our sponsor Frenetic for their support. Frenetic is a company that uses artificial intelligence for the optimization of power converters. You can try their software for free by using the link provided in the description of this video. So the point of this video today is to introduce to you some improvements that we have made on the induction motor model that we presented in these previous videos, Qspice number 14 and Qspice number 15. So the issue that we can see in this model is that when we look at the flux linkage calculations, we can see that we are getting a DC level in them. Here we are calculating the fluxes in the three phases. We are plotting them on this window and we can see that they have different DC levels when they should not have any DC level in a steady state. In any case, during the rest of the calculations, somehow this DC level compensated. So at the end we were getting the correct value for the electromagnetic torque and for the speed and so on, because we have tested that everything was okay. The results were matching the theoretical results. But in future simulations, we will want to see the fluxes, and then it's better to generate the fluxes without any DC level. So let's investigate this a little bit further. So the issue that we are having in the model is that we were using here ideal integrators, and these ideal integrators have a very high DC gain. Ideally, the DC gain is infinite. So this is the reason why they are generating DC values at the output. We would have to make very long simulations to find the steady state. So in order to get quickly the steady state, what we can do is, instead of using an ideal integrator that has a response like this one, the gain of the integrator as a function of the frequency is like this one. So what we are going to do is to use non-ideal integrators. So these integrators are going to have a low frequency pole at this frequency. So the DC gain of the non-ideal integrators is limited, and this will allow us to get steady state more quickly. In order to implement non-ideal integrators, I think that the easiest way is to do it like this. We are using a behavioral current source, generating a current with the voltage that we want to integrate, inject this current into a capacitor, and then using a resistor in parallel, we can implement this cutoff frequency. So we are using 1 farad for the capacitor and a value of the resistance equal to tau. So tau is going to be the value of the time constant of our integrator. In this way, the cutoff frequency of the integrator is going to be given by this expression. And for example, for a value of tau of 0.1 seconds, which is the value that we have been using in these simulations, we get a cutoff frequency of 1.6 Hz, which is much lower than 60 Hz. So the frequencies that we are going to handle in these simulations are of 60 Hz or 50 Hz and beyond, of higher frequencies. So the point is that we have to operate our integrator in this area. We are integrating frequencies in this part here of the response. So the non-ideal integrator at these frequencies at the end behaves as an ideal integrator because we are far away from the cutoff frequency of the circuit. So here we can see the issue that we have when obtaining the values of the fluxes. Let's remove this and plot, for example, the flux in phase A. So we can see that we are not getting a zero DC level in the flux. We have a DC component, and also in flux B and flux C, we can see that we have these DC components in the fluxes, due to the use of these ideal integrators. But in any case, the values of the electromagnetic torque was correct, and the value of the speed here is also correct. So this was compensated somehow when doing these calculations. Now let's see the results when we are using non-ideal integrators with a tau constant as shown here of 0.1 seconds. So let's remove here the angle and add the fluxes, this point and this point and at this point. So we can see that now we are getting in a steady state 0 DC values for the fluxes. You can check this by doing the average, so we can see that it's almost 0. So here is the final description of the model for the generation of the new component. We have included the non-ideal integrators, and also another improvement that we have done is to include here the voltage between both terminals of the phase, not only referred to ground. So the voltage that we are using is between this terminal and this terminal of the phase, because not always this terminal is going to be connected to ground. Maybe if we want to do a triangle connection of the motor, so this could be interesting. So this is the updated component. We have called it IM1. Here we can see the complete description, which is embedded into the definition of the component, and we have left the time constant tau as a parameter, so we can adjust it if necessary. Here we can see a test of this new component. So as you can see, now we have available the fluxes of the three phases in the component, and on the right we can see the results. We have the fluxes, these are the voltages in the different phases, the electromagnetic torque, and the speed. So we can see that right now we don't have any DC value in a steady state, and everything looks nice. These are the results that we were expecting for the electromagnetic torque and for the speed of our motor for this particular case. So this model is going to be available to everyone. Here is the link from which you can download it and test it. Well, this concludes this video today. I hope that you find interesting this model. Please let me know if you have any comment or question. Thanks for watching, and I hope to see you in the next video. Goodbye now.